All right, let's go. All right, last year we kind of went through some of this stuff. Right, well, last year we went through some of this stuff, right? We talked about charges being positive or negative. We talked about the fundamental charge. We talked about like charges to repel, unlike charges to attract, and so on, right? We looked at charging by friction and charging by induction. We went through these examples here of applications of electrostatic phenomena, right? And we looked at the precipitator and so on, and asked it to kind of look over the light conductor, right? Today we want to start on the new stuff. It's the electric field, right? Should you remember this? If you have an electric charge, around the electric charge, there's a what? There's an electric field, right? And the electric field is defined as what? The region around. The electric field is defined as the region around any electric charge when electric force is experienced. Okay? So if I place an charge here, it'll experience an electric force, right? It'll experience an electric force, and that region must have an electric field. That's okay? Anybody remember the direction of the electric field? Right? So what would be a good definition for electric field direction? Positive to negative. Yeah, it go towards the negative and away from the positive. So what would be a definition all the time for direction? What's a good definition all the time? Okay. I think so. No, I hear you. How you will define direction, not electric field. How you will define direction? Huh? Electric field, positive, negative. All right, close. Here's the definition. Right? Definition is right here. If you look here, I give you a small definition. The direction of the electric field is taken as the direction of the force exerted on a positive charge placed at that point. Think about this. I want to get the electric field around that positive charge, right? If I place a positive charge here, what direction will it move in? Towards or away? Away. So therefore, the electric field is away from the positive. Suppose I had a negative charge and I place a positive charge next to it. What direction will that positive charge move in? Towards. That's okay? The definition is the direction in which a positive charge will move. That's okay? So although I give you these notes, you still write it down. Every now and again, write down the important things. It might help you remember. It might. Right? Write down those important things. And the important thing there is direction. Right? That's the important stuff. Right, let's make a note of this. Okay? Bye-bye. Right, now for the important thing, electric field strength, right? Before we wrapped up last class, I told you electric field strength is very similar to what? Very good. Gravitational field strength. So every time we do something in electric field strength, I'll always compare it to gravitational field strength. Okay? Anybody remember what is gravitational field strength? Yeah, formula. From a formula, we can come with the definition. Huh? No, that's because of gravitation. What is gravitational field strength? How do you work out the gravitational field strength? F over what? Yes, Andy, you almost say halfway there. F over what? F over F, very good. Force acting per unit mass. You okay with that? Force acting per unit mass. So therefore, what will be electric field strength? Very good. Force over charge. That's the way you remember these things, right? Hopefully you remember this. So therefore, you should remember electric field strength is force acting per unit charge. Very good. Yeah. Very good. Good job, Andy. You're halfway with it. All right. So electric field strength is the force acting per unit charge, right? Minus. Here, right? So electric field strength is the in an electric field is the force acting per unit charge. If you can't remember definition, remember the formula, put it in words. All right? Force acting per unit positive charge at that point. What's the SI unit? Newton per coulomb. Right? But how about next SI unit here? Anybody think that they could derive or prove that that is right? Using the dimension analysis. See if we can prove that now. Electric field strength is Newton per coulomb. Where did that volt per meter come from? Right, I give me a minute. Right, book now. Where did that FM come out? I mean, VM come out from? How we get volt per meter? Capital V to volts, right? How they went from Newton per coulomb to volt per meter? Try something now. There's no more Newton and there's no more coulomb. So we have to find out way to get rid of that, right? Newton is what? Force, right? I'll give you I can use something with work and charge. Work done is what? Huh? Q over T. That's one volt, force by distance. Aye. Let me give all that hit. W is equal to, well, not W. Not yet, you think it's a W is equal to Q by V. 5. 2 back. W is equal to Q by V. And you can also use W is equal to force by distance. See if those two will help you. I'll give you a minute again. Anybody guys online? Right. Hold it, please. All right, let's check out the math skills now. Right, so electric field strength is equal to force over charge. Based on this formula here, force is equal to work done over distance. Okay? So force is work done on distance divided by Q. But if you look up here, I told you that work done is Q on V. So that'll be Q on V all over D divided by Q. And the Q will flip up here, and you will get QV all over D by Q. All after the Q's. Q cancel, and you will get V over, and D is in what? D is in volts, and N is in, sorry, D is in meter. Right? So based on dimension analysis, these two are correct. Anybody can tell me next definition for electric field strength? The first definition is, what is here? Force acting per unit charge. What could be a next definition for electric field strength? Look at the SI units. Look at the SI unit there. Michelle, any guess? Huh? Put it in words. Volts per unit distance, right? Yeah. So let's see where that comes in, right? So yes, volts per unit distance, so volts per unit meter. All right, and I'll show you where it actually comes from, right? Everybody write it down. Right. So you can write it. Go ahead and write it. All right. Before I show it back, I want to show you one thing. Watch this here. Look at this here. There is an electric field. There is an electric field between these two plates, right? And the strength of that electric field is based on the potential difference and the distance between the plates. Well, you see that? So the electric field strength between two parallel plates is the potential difference divided by the distance between the plates. Okay, so that is where the volt per meter came from. Okay, so the electric field strength is based on the potential difference between two plates. One and two. Both units in school, one here. You do it two in school, right? Yeah. One. Right in school, right? Yeah. All right, nice. Let's go back there. So I wanted to show you about electric field strength. Some calculation shortly, right? So you're going to see how to go through this. Right, something that's very, very important with electric field strength. If you didn't write anything, write this down. Electric field strength is a vector quantity. Okay, what does that mean? Right. So here's what that means. If I ask you to find the electric field strength, right? If I ask you to find the electric field strength on a charged particle, right? And there are two electric fields acting on it, then we need to find the algebraic sum. Of course, one direction positive, one might be negative. So because it's a vector quantity, we have to find the algebraic sum of all the electric field strength acting on it. Okay? So therefore, we'll do something like this, right? At E1 plus E2, one will be negative. So we have to consider the signs now when we're working out electric field strength. Right? We're going to do a few of these now, right? Well, in a little while. So remember, vector quantities are those that have magnitude and direction. Okay? Please remember that, sir. Once you're doing electric field strength questions, you have to remember it's a vector quantity. All right? Next one, calculation. Just now. Electric field lines are represented by electric field lines. The direction is the direction of a positive charge placed at that point. The field line direction or the tangent to it, if it's a curve, is such that the direction of the electric field strength, right? I'll show you that just now. The number of field lines per unit cross-sectional area is proportional to the field strength. So if you look here you have the direction, electric field lines along a positive charge. Right, see how uniform they are, and they're going away from the positive charge, right? Here, uniform again, nice even space in between all of them. Negative charge towards, unlike, sorry, there's a mistake here. This is like charges what? 12, and unlike charges, right? There's a mistake, right? That should be unlike. That's okay? Right? Just in case you forgot how to do that, catch them quick. Catch one of them alone. Right? So you can catch it online. Right? Because you should know the others. But I don't think that's for granted. Sweetie no, right? Sweetie no. Yeah. Don't the chat. But as for now, you have to go through everything. Don't worry about never open up. Andy? Okay. Hold up. Who's that? Andy, what are you doing? Andy, can I do my work from a place? Come down now.
Yes, that's good.
Ready? Join, sir. Ready? All right. So let's look at this one, right? Let's look at this one. Let's say on this negative charge, there is a force. There is a force of 10 newtons acting on that charge. Okay, and that charge, to simplify it, let's say the charge has a value of 2 microcoulombs. Right? What will be the electric field strength of that charge? Micro, right? It will be what? F on Q, right? Nice and easy, right? So that will be 10 newtons divided by 2 by 10 to the minus 6. So that's what? 5 what? 5 right? So like, let me do simple mega because that was kind of weird. 5 by 10 to the 6. What's the SI unit? Newton per coulomb. All right? So that's just a quick little way of how to work this out, right? What direction will the electric field strength be in? Check by definition. What direction will the electric field strength be in? If a positive charge is placed there, it will go one direction. Right. So the electric field strength is exactly what is seen there. Towards the negative, right? So the electric field strength is towards the negative charge. It's not seen. See that? Sorry. Towards the negative charge. All okay online there? Need it? Here, all okay there? All right. So there's a quick little thing to let's show you how it works, right? That's how we'll do the real calculation, right? I have to give you one more little formula. Here, we talked about this. We talked about this a little while ago. If I give you two parallel plates, and you find the potential difference between these plates, and we know the distance between the plates, we can find the electric field strength beyond D. That's okay? Quick question. If I want to strengthen the electric field, what to do? Bring them closer or increase the potential of one of the plates, right? Okay, nice. Good thing for you to practice. Right. Now for the load that we kind of waiting to reach here. Right, somebody brought it up earlier. Richie, no, Adam. He said, and you brought up a law earlier, Newton's law of gravitation. Right, you all remember this law? Newton's law of gravitation talks about two masses separated by a distance r.
Wow.
I say Adam. I said Adam. Right? Right? You remember this?
Yeah.
Right. And as I said, everything that happens in gravitation happens in electric fields, right? So if I have two charges, Q1 and Q2, separated by a distance r, there's also a force between them. Right? That force is called Coulomb's law. Okay? The force is called Coulomb's law. Formula looks very, very similar. Right, the formula is Coulomb's law. Right, so if you have two charges, Q1 and Q2, separated by a distance r, right, then this here is the formula. I didn't get it right symbol. Here. It's 4 pi epsilon r squared, right? What epsilon again? It's called the permittivity of free space, right? 8 what? It's called the permittivity of free space. It gives you an idea of how a particle can move through a medium. So like some mediums, it can move through easier than others. So if your permittivity is high, then it's advanced. Huh? Right? Epsilon naught, right? See that? All right, so
scientific purposes.
online, you all see the camera? You all see the whiteboard online? You all see the whiteboard in the wrong direction. I don't know. I don't this camera now. No, all boy time. That's the wrong camera. This camera like still not working. Huh? not sure. Next one, not sure. But we had the same problem Wednesday. Try to fix it, but so I take it off and put it on. All right. Anyway, so let's take a look. Before I move it, actually let's do some calculation. Sorry. Yes, I like it. So if we look back at whatever minute this is, it was. Right, let's go. All right, last year kind of went somebody stuff. Right, well, last year somebody stuff, right? Talking about possible negative. Huh? I don't know. It's started play every time I do that. Right. Anyway, right. So I'm going to give you two. I am going to give you two charges. Let's just start playing around with the numbers and we start to make it a little more challenging, right? Separated by a distance 2 by 10 to the minus 5 meters. Let's make it a little larger. Right here is 4 microcoulombs and here is 10 microcoulombs. Let's see if we can find that. Right? What was our epsilon again? 8 point? 10 to the minus 12. You've seen that there? Yeah, right. Try that, please. Try that there, please. Hello? Right? What you got? Right, learn to use exponent. Some of your still. Right? What we got? Right, that'll be Q1, Q2 all over 4 pi epsilon r squared. Huh? K, like you got 1 on 4 pi epsilon, there's nothing wrong with that. Right? So you'll end up with 4 by 10 to the minus 6 by 10 by 10 to the minus 6 all over 4 pi by r squared. That'll be 2 by 10 to the 5 squared. What's that? 9 by 10 to the minus 12. Yeah. Everybody okay with that?
Yes. Yeah.
Let's check out one line here. Where you got that? Where? You got that value where? Where? Are you there, where? Yeah.
Right. Hey, good job. Yeah. I remember.
All right. So you want to work out? What is it?
So that's all.
Sounding weird. Very hear me good now? Very?
Yeah, good.
Oh, okay. Everybody else can okay online? Grant. Karina. You hear me okay? Right. So suppose you want to use this same relationship to find electric field strength. Right? So here's our action. We know that F is equal to Q1, Q2 over 4 pi epsilon, or By the way, I didn't point out this, right? In front of the particles, there's give you the value for epsilon, but they also give you the value for 1 on 4 pi epsilon. Right? Yeah, K. So you don't have to keep something over that, right? What was the value for K? 9 by 10 to the 9. Right, so we know that F is equal to Q1, Q2, all over 4 pi epsilon r squared, and E is equal to FQ. All right, so if we need to find the electric field strength of the point, the electric field strength of a point charge Q, let's see how we're going to use these two relationships to help us out, right? Remember, electric field strength is equal to F on Q, right? F is what? F is Q1, Q2, all over 4 pi epsilon r, right? Let's say one of the charges is Q and one is small q, right? Let's change up this slightly. One is big Q and one is small q, right? And you divided that by Q. What will happen here? What will happen here? The Q will cancel, right? So it means that the electric field strength is equal to Q over 4 pi epsilon r squared, right? What does that mean? It means that the electric field strength of this Q is dependent on this Q. You are seeing that? What's the formula? The electric field strength of this big Q here is dependent on this small q. Okay with that? And for vice versa, the electric field strength of this small q would have been dependent on big Q. Okay? So if I ask you to find electric field strength, you need this relationship here. Right? So let me just clean it up a little bit. Right? Copy down there and see now. Copy down there and let's see if we can apply this relationship. All right, so this was all right. We'll just here now jumping in there, right? Are you on class? It's been half past it. But now that's finished. And then taking wrong class. Now you know your message. Right? Everybody ready? Right. So here's the challenging part that we're going to focus on now, right? Everybody right there? Finish? Right. So watch this here. Ready? You are ready? So let's say I give you a charge, and the charge is 10 coulombs positive, 10 microcoulombs, right? I would like to find the distance, sorry, the electric field strength at this point. Let's call it point A, and this is 2 by 10 to the minus 2 meters away. Let's see if we can find the electric field strength at A. How are we doing that? What's the relationship we're going to use? Right? E is equal to Q over 4 pi epsilon R squared. I'll look at that one line. That's the electric field strength at A, right? What direction will that be in? Towards? It's a positive charge. Away. It's away. Right? Direction is away. Why? If you place a positive charge there, it will repel, so move away. So look at that. Yeah? Plug in the values somewhere again. How I can make this harder while you're writing? How I can make it harder? Give me a next charge. And then after the final electric field strength, what you'll do? What will I do? Think about it because I'm going to do that now. Nausea. Nausea. Very thinking. Find the electric field strength at E. Granted it. Wait. One. Oh wait, it's some other line. Wait, are you okay there? Check back in case. Sure. Right, so you're plugging in Q, which is positive 10 by 10 to the minus 6, all over 4 pi by 8 points. I know, right? Right, 8.85 by 10 to the minus 12 by what again? By 2 by 10 to the minus 2 squared. How much was that? 2.5 by 10 to the 2.25 by 10 to the 8, right? And the SI unit is? Times coulomb, right? I am going to add an next charge. Ready? tell me what will happen here. Right, Adam? I'm going to connect charge here, Adam. And it is minus 10 now. Minus 10 microcoulombs. Okay? And the distance between them is 0.01 meters. You see now? Distance 0.01. Right. What will be the electric? What will be the electric field strength at A now? For the blue charge. Value is 0.01 now. What you will do? Same formula, right? Same formula. Right. So what direction will the electric field strength be in? Towards the right. So what am I going to lead up to? What am I leading up to now? One is to the right, right? Right, sorry there. So same formula, epsilon r squared, right? And sorry, that's Q. So that would be minus 10. What does the minus indicate? Opposite direction, right? So it's minus 10 by 10 to the minus 6 by 4 pi, 8.85 by 10 to the minus 12 by 0.01 squared. And I got 1 point. What's that again? Oh, sorry. What's that again? 8.9 by by 10 to the minus 6. Right. Oh, no, it's how come it's so different? By 10 to the 10. Right, here's the problem. I am going to ask you now for the electric field strength at A. Final electric field strength. The first one was due to the positive charge, the second was due to the negative charge. How are we going to find the final electric field strength? Right, what we're going to do is take the electric field strength here, 2.25 by 10 to the 8, and add it to minus 8.9 by 10 to the 8. Right, it's like finding the resultant force. Right, because remember this, right? At A, you have an electric force acting this way and an electric force acting this way. So therefore, the resultant is the electric field strength. Okay with that? How much is that? Negative what? Negative 6.65 by 10 to the 8. All right. So I just kind of break it down for you. If you're going to try a positive one out. Same concept. Any questions online? All right, let's try this here. No, not paper one. Yeah, paper one. Try that, please. Same concept. Number change, right? So, take your time, plug in the values. Very good there.
That is over here. That's it. Okay. So you want the electric field strength at the middle, right? Let's call that point E for now. Here to here will be 10 centimeters. Here to here will be 10 centimeters. Right in the middle, right? So let's find the electric field strength to the 40. Actually, I just leave it a little bit different, right? I'm going to call here Q1 and here Q2. Right, based on my label in there, what direction will Q1 act in? Towards the 40 or away from the 40? Q1 is what? It's like E1. But act towards the 40 or away from the 40? The electric field strength at this point here. Will it act towards the 40 or away? So that I label it as E1. But what about the electric field strength to this one here? Towards, right? So it will be acting this direction. Andy, you okay with us? Right, so they are in opposite directions, right? So one will be positive, one will be negative. So work it out some more again. 40 by 10 to the minus 6 all over 4 pi by 8.85 by 10 to the minus 12 by 1 centimeter, right? That's 0.1 squared. What's your for E1? 3.595 by 10 to the and that's okay. And next one.
Minus 8.99 by
26. Okay. So therefore, the electric field strength that they absent for will be E1 plus E2. Right? And they already have the sign conventions already. So that's 3.95. They already carry the sign plus or minus. Right? How much you got? 2.7 by 10 to the 7. 2.7 by 10 to the 7. Very confused there? Here any kind of values? All? Are you okay with that?
Yes.
Then press number one more part underneath. Press number next part underneath. Any questions online? Indicate on the diagram along the line joining the 2 points the approximate position where the net field is 0. Where is that? No, just prove that the middle is that value. Where would it be? Doesn't have to be the exact value, right? Actually, I simply call it calculated. That's a good idea. Huh? Actually, we're going to calculate it. So know where it should be, though. To the right somewhere? To the left somewhere? To the right? Think about it, right? I'll give you a minute. But I want the exact position. Huh? Where would it go? And I'm going to make it work out the exact position, right? We have to figure out where will it go. You want what do you want to happen? Online? Anybody? What do you want to happen? For the electric field strength to be 0. What has to happen? Huh? Cancel off, right? So the electric field strength 1 has to be equal to the electric field strength 2. How to go? Right? So we can show it by calculation. Right? What we just said. We just give the answer. Both electric field strengths have to be equal. Make them equal and solve the answer. Right back. Let's find it. That's all I wanted to hear. But not here, but I want to see how you all come up with where it's going. Somebody sit at it. RSC on dude. Watch this here. I want to join the board, but I can't. Alright, here we'll do, right? Okay, I have the original here. What? No, don't do one here. No. Right, watch this here.
We have the
Thank you very much.
right? Here is 40 minus coulomb, and the next value was minus 10, right? What is here? We do not know, right? We do not know exactly where it has to go, right? But we have an idea. Right? But we know that we have to make I don't have the values. What was you want again earlier? That was due to the 40.
Yeah.
Right. What was it? Right, 10 to the 7. Next was what? Right. So we recognize that E1 is larger. So we have to make E1 smaller and we have to make E2 larger. So where do we go? Do we go closer to the minus 10 or closer to the 40? Closer to the sure? You want to make it denominator smaller, right? But remember the formula. E is equal to Q over. So you want to make R. You want to make R smaller. Okay? So let's pretend we don't know the exact position. We're going to work it out. Let's pretend it's somewhere here. Right? That distance is X. What will be this distance here? Let's call that point A. So if A to minus 10 is X, what's the distance A to 40? 20 minus X. And remember the distance is 20 centimeters. So here will be 20 minus X. Sorry. Let's go to the SI unit, right? 0.2. Same here, I just add on the calculation part. So that's 2 over 1. Yeah, had no multiple choice no. Right. I don't think it was nice. So how are we going to handle this here now? We said Adam. Huh? We said that the electric field strength must be equal, right? Yeah. Yeah, no, wait. Right? So the set E1 equal to E2. Right? Or like a solve the rest. So here is Q over Q1 over 4 pi epsilon R squared is equal to Q2 by this R1 and R2. Right? Can I leave this out? Will that cancel? Yes. It's a constant, right? Q1 is 40, so that's 40 by 10 to the minus 6. R1 is what? 0.2 minus X. 0.2 minus X squared. And Q2 is minus 10 by 10 to the minus 6 all over. Right? The magnitude don't matter, so we got a negative sign. By X squared. Cross multiply, make X squared subject to the formula. Everybody follow why I did this? Andy? Why I did that? Why I made them equal? So that E will be 0. So that the final electric field strength will be 0. Okay? And why did I call one side X? Because I don't know that actual position, right? Copy it down. Somewhere again, I will. Yes, it will be 40x squared by 10 by 0.2 minus x squared. We can divide it out, you'll get 4x squared is equal to 0.2 minus x. You can square both sides, and you'll get 2x is 0.2 minus x, do a little maths. 3x is 0.2, x is 0.2 over 3, which is just cross multiply with them. Right? By 0.2 divided by 3. 15, which is how much? 0.1. 0.66. Right? So ideally, it should go very, very close to, in fact, let's put it in centimeters. Give us 0.066. So let's say 6.6, right? 6.7. Let's say 6.7 centimeters. Okay? So it's much closer to the next one. Okay with that? Right? For the people, for the maths in it, watch it here. When I set it up, right? I just cancel out everything out constant and cross multiply. Right? And then I square both sides. When I square both sides, square root both sides, I got this. Right? And then I solve for it. I look at maths, right? Right, next day we'll do a few more where I will change the direction of it. All right.